Hello everyone, welcome back to another video. Today we're going to be looking at and going over the 2019 AP Chemistry exam question 1. Before we get started, I just want to remind everyone that our website studystem.org is about to be starting its free online tutoring for the upcoming semester. If you need help in chemistry, physics, and biology, head over to our website studystem.org and you can look at our live tutoring schedule and come and join free of charge. This is purely to help high school students reach their educational goals. Now, let's examine the problem at hand. So we start off by being given a molecular structure, and we're told about the compound urea, and we're told that we're given the complete Lewis electron dot diagram for the molecule urea. So the first question is a hybridization question, and it asks us to find the hybridization of the carbon atom in the urea molecule. So the carbon atom is going to be right there in the center. And to do this, we're going to need to add up the number of atoms plus the number of valence lone electron pairs. However, this carbon atom does not have any lone pairs, so we don't have to worry about that at all. Instead, we can just look at the number of atoms. Because this carbon is connected to 3 atoms, it's going to have sp2 characteristics. And why is it sp2? Well, if a carbon is joined to 4 atoms, then it's going to be sp3. If it's joined to 3, then it'll be sp2, and if it's joined to 2, then it'll just be sp. And note, if this carbon had 2 lone electrons, even though it's only joined to 3 atoms, it would still be sp3 because you add up the number of atoms and lone pairs. But for this first part, the answer is just sp2. For part B, we're told that urea has a high solubility in water, due in part to its ability to form hydrogen bonds. A urea molecule and 4 water molecules are represented in the box below. Draw one dashed line to indicate a possible location of a hydrogen bond between a water molecule and the urea molecule. So this is a electronegativity question, and to help simplify what they're asking in this question, I have inserted a periodic table on the left. So let's look at that for a second. So what you have to realize is oxygen is over here on the periodic table, while hydrogen is over here. And electronegativity characteristics increase as you go up the table and increase as you go over on the table. But the importance for this is that the electronegativity of oxygen is going to be higher than the electronegativity of hydrogen. So if you have a water molecule, like I drew over here, the electrons are going to be moved that way, which will make these hydrogens partially positive and this oxygen partially negative. So knowing that, we can see that a partially negative oxygen is going to be attracted to a partially positive hydrogen. So here's the urea molecule in the center, and again, these hydrogens are going to be partially positive and these oxygens are going to be partially negative. Can you see where I'm going with this? The answer to this question is to draw a line between the only logistical spot that has a partially positive and a partially negative atom connected, which is right here. Because if you draw a partially positive to partially negative line, like here, that wouldn't make sense because neither of those are partially negative at all. However, you could also draw a line such as this. But the answer to part B is going to be drawing a line between the oxygen of one atom over to the hydrogen of another atom, because this hydrogen is going to be partially positive and this oxygen is going to be partially negative. For the next part of this question, we're told that the dissolution of urea is represented by the equation above. The student determines that 5.39 grams of urea can dissolve into water to make 5 milliliters of a saturated solution at 20 degrees Celsius. So for part C, we're asked to calculate the concentration of urea in moles per liter in the saturated solution at 20 degrees Celsius. So we're told that 5.39 grams is the amount of urea that's used. So we have 5.39 grams, and that is going to be first converted into moles because we're being asked for moles per liter. And we're told that the molar mass of urea is 60.06 grams a mole. So then we're going to multiply that by 1 over 60.6 grams. And at the top we have moles, 60.06. So now if you multiply that out, you have the moles of urea that are used, which will equal 0.0897 moles. However, we're asked for moles per liter. So the next step is dividing this moles by the amount of liquid we have, which is going to be 5 milliliters. So 5 milliliters is equivalent of 0.005 liters. And if you divide that out, 0.0897 divided by 0.005 liters, you'll get 17.9, which is the concentration, so it is in molarity. And that is the answer to part C. For part D, we're told that the student also determines that the concentration of urea in a saturated solution at 25 degrees Celsius is 19.8 molar. Based on this information, is the dissolution of urea endothermic or exothermic? Justify your answer in terms of Le Chatelier's principle. So for me, the easiest way to justify this is think about what the student is saying is going on here. So up here, the concentration of urea in the saturated solution is 17.9 at 20 degrees Celsius. So when we increase the temperature by 5 degrees Celsius, we increase the concentration of urea in the solution. So down here, I wrote out the equation that we're given up at the top, way up here. So this equation is going to be able to be looked at from the perspective of Le Chatelier's principle, and the fact that if we modify one side, we will return to equilibrium is the key to solving this problem. So what we have to realize is that if we add heat, when we add heat, so if we add heat to this side, then it will increase this way and the concentration of urea in the saturated solution goes up. So that makes sense because we're not having an increased concentration at a decreased heat. If that was the case, then heat would be on the other side of the equation. But rather, heat is on the left side, and then the concentration of urea in the solution is on the right side. So when we add heat to the left side, it increases the concentration on the right side. So because of this, we're able to determine that the dissolution of urea is endothermic because we're adding in energy. So the answer to part D is simply that the dissolution of urea is endothermic, and the justification for that is that when we add heat, the equilibrium is altered so that there is a higher concentration of aqueous urea. For part E, we're shown a bunch of pictures of different lab equipment, and we're told that the equipment shown above is provided so that the students can determine the value of the molar heat of solution for urea. Knowing that the specific heat of the solution is 4.18 joules per gram Celsius, list the specific measurements that are required to be made during the experiment. So to the left, I have the two equations that we're going to need to use, or at least look at, in order to solve this problem. And these equations come directly from the concept of molar heat. Molar heat is simply specific heat divided by the number of moles. And molar heat is the amount of energy needed to raise 1 mole of something by 1 degree Celsius. So in order to solve this, we're going to first need to look at what is in this equation, and then we'll need to look at what's in this equation, because this is molar heat. So we can move around this equation. If we start with Q equals Q, which is heat, equals mass times the specific heat multiplied by the change in temperature, we can change that by moving around variables to the specific heat equals the heat divided by the specific heat, the heat divided by the mass divided by the change in temperature. And we can plug this in over here. So we'll get the molar heat will equal the heat divided by the mass divided by the change in temperature all over the number of moles. So now the question is, what are we going to need to solve this? So the variables we're going to need is, first of all, the number of moles. And for number of moles, we're going to be referring to the number of moles of urea. And we're going to need the balance for that, which is going to give us the mass of the urea. So the first thing we need is mass of the urea. The second thing we're going to need is also from the balance, and that's going to be the mass of the water. Because we're told the specific heat of the solution, but we need to know how much water is used in order to be able to find the molar heat of the solution, because again, we're talking in moles. So we're also going to need to know the mass of water. And lastly, we're going to need two other things in order to be able to calculate the molar heat. We're going to need the change in temperature of water using a thermometer. So in order to find the change, we're going to need the initial temperature of the water, and we're going to need the final temperature of the water. And if this is a confusing explanation, I encourage you to look at the equations at hand and see how, in order to find molar heat, we need all of these things. Mass, so that we can calculate moles, and the initial and final temperature of the water, so we can calculate the change in the temperature. So the answer to part E of question 1 is that we're going to need the mass of urea, the mass of water, and the initial and final temperatures of the water. And please note that the final temperature will be the final temperature of the solution. So for part F, we're given a table, and we're told that the entropy change for the dissolution of urea is 70.1 joules at 25 degrees Celsius. Using the information in the table above, calculate the absolute molar entropy of aqueous urea. So to solve this question, we're going to need the equation that I wrote below, which gives us the change in entropy of a reaction. And we're told that this is equal to 70.1 joules divided by moles times Kelvin. However, you don't need to worry about those units right now, and you can simply think of 70.1 equals the sum the entropy of products minus the sum of entropy of reactants. And we're actually given the sum of the entropy of the reactants, which is this number right up here, because this is a question about the dissolution of urea, so it will be going from a solid into an aqueous solution. So we have 70.1 equals the sum of the entropy of the products minus 104.6. And this means that the absolute molar entropy of aqueous urea, we just move that 104.6 over there, and we end up with 174.7, which is going to be the answer to this question. So I hope that makes sense. We use the equation to calculate the change in entropy, and we simply plug in the two values that we have, and we can find the third value. So the next part is based on entropy again, but it asks for particle level reasoning of why the dissolution of urea in water is positive. And I think of this question, I base my answer to this directly based on the concept of entropy and the idea of entropy that we're all told in high school, that is, entropy is equivalent to a messy room. And higher entropy is going to be a messier room. And things have a tendency to increase in entropy or messiness over time, and it takes work to return them to their normal states. So the reason that the entropy is positive for the dissolution of urea in water is because urea in water is going to be much less organized. And when urea is in a solid form, it's going to be all packed nice and tight. But when it's in water, it can be all over the place. So that's why the entropy is higher over here. So the entropy is increasing and is thus positive for the dissolution of urea in water simply because it's more messy. There's a greater number of combinations of urea molecules in water, which corresponds to the positive entropy. So the last part of question 1 of the 2019 AP Chemistry exam says that the student claims that the change in entropy for the process contributes to the thermodynamic favorability of the dissolution of urea at 25 degrees Celsius. Use the thermodynamic information above to support the student's claim. So for this question, we're going to be dealing with thermodynamics, and we're going to be using this equation I drew out right here for Gibbs free energy. And the variables in this is on the left we have Gibbs free energy, and then on the right side we have Gibbs free energy is equal to enthalpy minus temperature multiplied by the change in entropy. So the student's argument is specifically about entropy. So for this question, it's important to remember that if Gibbs free energy is negative, then this is spontaneous and is thus forth thermodynamically favorable. So this question is a slightly weird question because you have to look at the equation and logic it out. In order to make this negative, enthalpy is going to be positive, but temperature is also always going to be positive. Enthalpy can be positive or negative, but you actually don't have to think about whether it's positive or negative at all because that does not change the thermodynamic favorability for this question. So temperature is going to be positive. So in order to make this as negative as possible, we're going to need to make entropy as large as possible and as positive as possible. And then this will lead to enthalpy minus a positive number equals Gibbs free energy. So if entropy is large and positive, then the dissolution of urea is going to be more thermodynamically favorable. So the answer to this question is going to be that the positive entropy leads to the reaction being more thermodynamically favorable. and that is, of course, for the dissolution reaction. So the answer is simply what I drew up there. Thank you so much for watching. Again, if you need free tutoring and help with chemistry, physics, or biology, head over to studystem.org and we'll be able to help you out there. If you found something in this video confusing or you need help on it, feel free to bring those questions to our live tutoring or drop a comment in the comments section below this video, and I'll be making videos covering concepts that high school students find confusing. So thank you so much for watching and have a great day.